Hello again, it's been a while. As those that watched my previous videos know, I'm making an attempt at demaking Super Mario 64 for the Game Boy Advance. If you've got questions, you might find answers to them in those older videos. Today I'll cover the changes since the last update. First up is a change a lot of people have been asking for: sound effects. Sadly, playing audio isn't as simple as calling a play sound function as it might be in a game engine like Unity. To implement this, I had to write an audio driver for the Game Boy Advance's sound hardware. Thankfully, the hardware is fairly conceptually simple. The Game Boy Advance has several sound channels, but the two we care about are the digital sound sample channels, accept 8-bit audio samples played at a constant but configurable rate. The DSP hardware, that is, digital signal processor, has a small internal queue for audio samples, so the audio's driver's job is simply to keep this queue filled with sound sample data quickly enough that it never runs out of data to play. It does this by hooking itself into a hardware timer interrupt, such that it's able to push data into the queue at a consistent rate no matter the frame rate. There's still quite a bit of optimization work to go, but it's already fast enough to make up less than 3% of the total CPU work. I've only added a few sound effects to the game right now, but it's enough to give things some character. There is also limited support for background music, although because this is currently sample-based rather than mixed using a sound font, it takes up a lot of ROM space, which likely isn't viable long term. Next up, billboards. They're commonly used in the original Super Mario 64 for a variety of objects. There's nothing too complex about their implementation here, other than that their shape is computed after transformation to screen space instead of before, as with most objects, allowing them to always face the camera. However, there is still some work to be done. They're currently using the existing triangle rasterizer, which does not support textures of a size other than 32 by 32 texels, and always tiles textures in both axes. In practice, larger billboard textures need to be supported. Another feature I've put some work into is depth sorting for objects and stage elements. As I walk up to this fence, you can see, as expected, that Mario appears behind it instead of in front of it as before. Implementing this correctly is more annoying than it might initially seem. Because the order of object polygons, like Mario, are determined ahead of time, it's necessary to incrementally progress through the stage polygons as you render them, stopping to draw an object when required. To get this working, I've switched away from pre-computed ordering tables in favour of a system of depth bins. Once a triangle or object is transformed to its screen space position, it gets placed into one of about 1,000 variable-sized bins, each one corresponding to a specific range of depths from the camera. When it's time to render the world, the game runs through each of these bins and draws their contents in order, resulting in a mostly accurate draw order. Needless to say, making this process fast was a challenge. Computers don't generally like dropping everything to go away and perform entirely different work. Next up, perhaps the most requested thing I've seen in the comments: texture warping. In previous iterations of the game, polygons close to the camera experienced some pretty severe warping artifacts. This happened as a result of a lack of perspective correction in the texture mapper. The fastest way to draw triangle pixels to the screen involves updating the texture coordinates by a constant, but this is in conflict with the perspective camera. Here's an example. I've given this rectangular texture a number of vertical bars. Each bar on the texture is an equivalent distance apart. Right now we're viewing the rectangle using an orthographic camera. An orthographic projection has no perspective component, meaning that the objects will always appear the same size no matter how far they are from the camera. When we turn the camera so that it's viewing the rectangle from the side, we see that each bar remains the same distance apart. This is great. It means that every time we move one pixel to the right on the screen, we only need to add a constant value to the texture coordinates in order to update it. But watch what happens when we switch to a perspective camera, like the one we're using in-game, that more accurately represents the way we see objects in real life. All of a sudden, the distance between each bar changes across the surface of the rectangle. Bars that are further away appear to be closer together. Solving this problem requires some careful maths, but the short and long of it is that we end up needing to perform a division operation for every pixel. Divisions are particularly slow for computers, especially for hardware as old as the Game Boy Advance, and so this is an unacceptable solution. During various experiments I found that proper perspective correction resulted in the game running between 2 and 3 times slower. There are a variety of partial solutions to this problem. The one I landed on was that which is used by PlayStation 1 games. The PlayStation's GPU is not capable of performing perspective correct texture mapping, so games running on it chose to subdivide their triangles into smaller triangles. Small triangles experience less visible warping, so by dividing several times over it's possible to reduce the warping effect a lot, enough that it stops becoming a major eyesore and instead turns into a quaint little retro effect. I've noticed a lot of indie games even choosing to add the effect back in recently. Such is the 20-year nostalgia cycle, I guess. To avoid cracks appearing between polygons of different subdivision levels, I ended up applying subdivision on edges, not entire triangles. This has a twofold advantage. First, I don't end up needing to apply unnecessary levels of subdivisions in both axes if a triangle is only being warped in one axis, which improves performance. Next, it means that all shared edges get the same level of subdivisions applied, meaning that you never end up with T-junctions appearing, which would otherwise result in mesh cracks. Here you can see the polygon subdivider in action. As polygons get close to the camera at grazing angles, they split into multiple child polygons in real time. Notice how this process is biased towards whichever angle the polygon experiences the most perspective stretching in. Next up, several new stages have been added, thanks to the work of 2 contributors. As with other stages, both have needed to go through a process of simplification and fixing in order to reduce the polygon count, merge geometry, and remove T-junctions to prevent mesh cracks. Last of all, I've been gradually working towards an entity system that will allow spawning objects like enemies, coins, and cannons into the game. The work for this is ongoing, but I've reached a design that looks like a much simpler and more memory-efficient version of the entity component systems used by modern high-performance game engines. I'm hopeful that just a small handful of components will allow me to cover the range of objects present in the original Super Mario 64. There's nothing to show for this one, but I'm hopeful that the next video will contain some rather interesting things indeed. That's all for today. Thanks for watching, and thanks for all of your inspiring comments on the last video.